All right, welcome back, everyone. We're going to continue our discussion from last time. We were working on backpropagation. First thing we discussed is the chain rule, how if you have a sequence of dependencies among variables and you want to compute the derivative of, let's say, z with respect to x, then you can do dz du times du dy times dy dx. Or you could actually skip over, just do dz dy dy dx. And we also said that if you have a graph like this, where you have several different variables at this node, that's what we mean by this set notation, that you need to use the multivariable chain rule, where basically you need to sum the different gradients across these different paths. And then we applied those ideas to the simplest case of our two-layer neural network, where we have the hidden layer looks like this, and then we have the output layer looks like this, and then that goes into the loss. And so we essentially said the forward pass, we start with the things we know at the beginning of this iteration of stochastic gradient descent, and then from those we compute, from these two things we compute this, using this we compute that, using these things we compute that, and then using these things we compute that. And those operations are listed here in the forward pass. Then to do the backward pass, we start at the loss and we move backwards, and we do dj dz That's something we can compute. And when we compute that derivative, we need to evaluate it at the point zo, which is actually something we computed in the forward pass. So you can see why we need to do the forward pass first. And then when we want to do dj dah, we can write that as dj dzo times dzo dah, but we're going to reuse this number that we computed last time, so we don't have to compute it again. So all we have to do then is compute dzo dah, and we can do that by looking at the relationship between them. And just from this equation, you can see dzo dah is just wo. And so that's something that we know because that was given to us from the last gradient descent iteration. And then we can move on to dj dzh through this operation here, and we can reuse the first part, which we just computed previously, and then we just have dah dzh, and we get that from this equation here. So once we have those gradients computed, we can move on to the gradients of the cost with respect to the parameters. So we could do dj dzo times dzo dbo. And in doing this, we can use the previously computed dj dzo, and then we just have to figure out what is dzo dbo, and from that we can look at this equation and see that it's 1. So we do something similar for dj dwo, dj dbh, dj dwh. Any questions on this procedure? Okay, no questions? All right, so that gives us kind of the general idea of what we're doing in the simplest case, where all the variables are scalar and the batch size is 1. Then what we said is, what if we have a batch size of b greater than 1? So now we can kind of visualize each of these nodes. I've expanded them into b scalar nodes. And if you think about it, based on the structure of the equations, essentially all of the processing is decoupled across the different i's. So that means you have like parallel paths here that do not interact. They only interact when you come to the loss, and then you have to sum over I. And also you could say they interact when you come to the parameters, because a single parameter like BO or WO, that affects all the batch elements. So basically we apply the same procedure as before, and for some of these things like this, we can see that we're going along that particular branch I, and we don't have to consider any other branches I. So that's why there's no multivariable chain rule up here. But then when we consider like DJ, DBO, we have to do DJ, DZOI, DBOI, but we have to do that separately for each of these, and then we have to sum them together over I. So that's where we see the multivariable chain rule showing up. Okay, so, but everything else is pretty much the same as the previous page. All right, is this making sense, or is it complicated? Making sense to everyone? Okay, any questions on anything? Okay, so then the last generalization was we have B items in a batch, but then we also have vector valued variables. So here I'm just thinking of these nodes now as containing a vector. And the dimensions of these vectors change. So like the xi's have D features, but then you might have a different number of hidden features or hidden scores at this layer and so on. In any case, this is what we have for the forward pass. So here we see like the relationship between the raw input features and then these hidden scores. Basically, we have a matrix multiplication and adding a vector of biases. So the things that change are when we do something like DJ, and we consider one of these elements within this vector. So we're fixing I, but we're also fixing an element in that vector. We'll call that element L. So we have, you basically, from that single L, we have to consider the paths through all of the entries in this vector here. So for that reason, we have a chain rule happening here. And that is reflected in the fact that this matrix here is mixing all these AHIs to give us our ZOI. So let's see. Is this making sense? Any questions on this? Yes.
So it goes through each batch and each element of the vector each time? Yes.
Well, yeah, so for when we do stochastic gradient descent, to do one update of our parameters, we definitely use all the batch elements. But then, we have a whole bunch of parameters, right? So these are parameters that could be vectors, matrices, and those parameters, we just need to know how are they related to our loss. And these equations tell us those details. And so yeah, I guess it's like you sort of need to trace through, like for example, if I consider these parameters in this matrix, these parameters you can see affect all the different batch elements, right? They affect this vector, then they affect this vector, And then this vector here, which has itself different elements, affects this vector. So I guess it's sort of like, for the purposes of doing this sort of derivation, you need to consider what stage you're at. Like, what are you trying to compute? And then for that stage, you need to maybe, based on this or based on a picture like this, try to figure out what's going on. Like, which variables are related to which other variables. So that's why here we were focusing on dj, d for a particular I and a particular L. So that's why I was, maybe this is the L we're focused on. And then you have to think, how does that, if I make a change in that parameter, how is that reflected in the loss? Well, if I change a single parameter in this vector, it's going to multiply this matrix, and that parameter, that Lth parameter, will multiply all the elements in the Lth column, and then those will affect all the elements of Z. So basically what that means is that there's connections from that L through all these elements, which we're indexing by K, and then all of those eventually go to the loss. Yeah. So that's why this shows up here. Okay, but then let's do a different one. Let's look at dj dzh I. And in particular, we're going to look at the Lth element of that vector. So we also have a vector here. We're looking at one of those elements here. But the way we're doing this, because we can do it different ways, but we're choosing to make our life easier, let's use the thing we just computed with one new thing. And so now when you think about this, when we look at the Lth element here, so we're looking at this equation, we're looking at the Lth element in this vector because of the fact that these activations only work on scalar elements. Sorry, I have to go back a ways. So I was looking for this picture. You can see that these are decoupled across all the scalar elements. So that makes our life easier. So that means that basically there are direct connections between those. So if I want to do, dj d this element, I can do dj that green one times this. And now there is no chain rule, or there's no multivariable chain rule because there's only one path. And so that's why there's no summation over here. Okay. So this is actually the only place that the summation over K shows up, but then we still do have the same summations over I that we did in the previous page for all the same reasons. So really this is the new thing. Okay, so that's most of it. I think if you understand this, then that's backpropagation. So generally speaking, this manifests when you have like a complicated sequence of things happening and you want to derive gradient updates in small pieces. Like if you tried to write like a single equation that relates this stuff to the loss, you could do so. You could have this massive equation. And then you could try to do calculus with that, like how you learned in high school, and you would find that it would just be massively complex. It'd be like chain rule over and over and over and over again because you have so many nested things. So the whole purpose of backpropagation is just to simplify that and just go in a step-by-step procedure that you can apply just as a kind of like an algorithm. It doesn't require a lot of technical sophistication. You just have to be able to, you split this up into steps. You just basically have to be able to do calculus for each step separately. You don't have to do calculus on the composition of all those steps. So, in a homework problem or midterm problem, I might give you another relationship. It might not be exactly this structure here, but it's also some relationship of multiple stages of things depending on things, and then, parameters located throughout, and then basically say, okay, how are you going to update those parameters? Just show me how you use chain rule to do that. And it's really just splitting it up and just taking it one step at a time. Okay, great. Any questions? Everybody good? Okay, so the very last thing to do is to try to write these same equations without things like summations, because as we know, when we want to implement this, we don't want to have like for loops over things to execute this. We also maybe would like to write this in terms of matrices instead of this for all I. So that's really the very last step here, is just writing this in a way that's more conducive to implementation. So what we're going to do, which is sort of what we've always done throughout the whole whole class, is if we have different samples in our data set, what we've done is we've transposed them, these are the feature vectors, and stuck those as rows of our big data matrix, right? So each one of these rows is one sample of the features, and then this is where we get our big X matrix. And we've been doing this back since, all the way since Unit 2. So we're going to do exactly the same thing. With our xi's, we're going to stack them as rows of a matrix. In order to do that, of course, we have to transpose them. But we're also going to do that with any quantities that have an I. So we can stack these as rows of a ZH matrix, these as rows of an AH matrix, these as rows of a ZO matrix, and then these as rows of a Y matrix. So here's those definitions. Except, okay, we're not going to have n. Because we're working with just a batch, we've split our total training set into a smaller batch of size B. So basically, this is going to be B. So here's another way of writing that. So I could write it like this, but that takes a lot of space on the page. So what I could instead do is I could transpose both sides of this. And when I transpose the right side, I get x1, x2, ... stacked as columns. Okay, so that's basically how we're writing it. So these are, again, these are just like the ways we've been creating our data matrices all term. And so basically, this equation, now I just imagine I'm stacking these one after another as columns of a matrix. That just turns into this. As for this term, essentially we just want to take this fixed vector BH and we want to copy it and stack those copies next to each other, right? Well, one way I could do that is I could multiply BH by a row vector of 1s, because that gives me B, 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 right? That's, if you want to just kind of copy and repeat something, just multiply it by a row vector of 1s. So here's the row vector of 1s, the boldface 1, and the little b means there's b, it's, b, the length of that vector is b. So that gives us expansion out like this. So everything else is pretty much the same, all those steps. Any questions on these? Yes?
From the previous one, here across the dash there are coupled, but in the next one, in the matrix code, they haven't coupled each other from, for example, I to...
Which part is coupled here?
I mean, can we write it down as coupled? similar output, everything in a matrix form?
I just don't know exactly what you mean by coupled.
Like from like one of the batch, one of the lines, if you have like cross from I and J, for example, they have a good relationship between them, with them AI and AJ.
Yeah, so we are collecting all the batch elements into all these matrices.
You know, in the upper one, the H and I are only related to XI, so it's not related to XI prime.
These ones,
Yeah.
they are related because it's like I took let's say I take maybe x1, and then I multiply by this and I get zh1.
But it's not related to the upper one, because I'm the next row in the batch.
Next, it's not related to.
In the upper line, they are not related to the, we don't have cross lines, they are the apartment lines.
Yeah, so I guess so this equation says that, what happens for a given I or a J not equal to I, you can write it as two completely decoupled relationships, right? And that is also manifested in the fact that these lines are parallel. And we're not changing any of that. So down here, this is just rewriting that. So if you look at what happens to the first column in X, it produces the first column in Z, right? There is no mixing across the columns of X. To do that, you would need a matrix to the right of X transpose. We don't have that, right? So this is hopefully, this is exactly writing this, but just packing the I's, stacking them like this. Okay. All right. Any other questions? Yeah.
What is the dimension of WH?
So it really depends on, okay, so the number of columns in WH is going to be the number of raw features. So in the example we worked on in this unit, there were 2. So there's 2 columns. This matrix has 2 columns. But then if you remember, we had four different hidden nodes, hidden classifiers, right? So this would be a 4x2 matrix for the example. So in general, this is one of the things we have to design when we design a network. We have to choose how many hidden parameters to use, right? So we just happened to choose 4 for this unit. We said 3 could work well too, 5 could work well, 2 couldn't work well. Does that make sense? Okay. Okay, so, all right, so hopefully we understand these. Now the only thing left is to look back at some of these other equations. Like for example, this one here. So we can think of this as the ith row and kth column of some matrix. And over here we can think of this as the kth row and lth column of a matrix. So if you imagine putting those matrices in here, noticing that K are the inner dimensions of both, and we're summing over K, that tells us we have exactly a matrix multiply, and that the output of this will be the ith row and lth column of this matrix. So basically, this equation just turns into a direct matrix multiply. The first matrix, we're writing it like this, dj, dzo. That's, sometimes we think of that, we write it with an upside down triangle. But that's just how I'm doing it here. Is everybody okay with that part? Matrix multiply? Okay. Let's look at this part. This is actually different. Here, all these matrices have exactly the same 2 terms, IL. So this is not a matrix multiply. This is an element-wise multiply of 2 matrices. So these matrices have the same size, and I take first times, let's say the top left times the top left, that gives me the top left here. Or the top right times the top right gives me the top right here. So that's a element-wise multiply. And probably the most common notation for that is this circle with a dot. It's called the Hadamard product sometimes, just an element-wise multiply between matrices. So in NumPy, that would be an asterisk, whereas in NumPy, this would be the at sign for matrix multiply. Okay. Okay. Any questions on this one? Okay. So then we have over here. Here we have a vector. These are elements, the kth element of a vector. Here we have a matrix, and we really need that. We want I to go this way, and then we have a vector of all ones. And so we want k to come down this way. So we said that if I is going across the columns, that must be a transpose of our data matrices. So over here we have transpose times this ones vector. And pretty much the same thing happens here. And then over here we have, again, matrix, matrix. But we want this I to be going across the columns if we're summing over I, so we need to transpose this matrix, but we don't want to transpose this because I is in the correct place. So down here we have transpose the first times the second. Okay, so basically that's it. That gives us rewriting everything compactly with matrices and vectors. More or less done. Any questions on this? Okay, so just a summary of what we have then. We have this forward pass, same as on the previous page. We have the backward pass written with vectors and matrices. And there were some details we said, how do we do these loss derivatives? Depends on the kind of loss we're working with. So if we have binary cross entropy loss, we know we have something of this form with, this is our binary cross entropy. And it's pretty, I think we actually did this back in Unit 5, maybe. When you differentiate this with respect to ZOI, you get this. And with K-area cross entropy, we have, we derived this as the loss, and then we also, I think, at one point differentiated and found this. So those are just examples of how this might manifest. Okay, so that's all we have for backpropagation. Any remaining questions or anything? Okay, great. So we're going to change gears, and we're going to talk about implementation with how do we implement these things. So the basic idea is that as we've learned, if I give you this computation graph, and I tell you the relationships, between the different nodes in the graph, then there's a very well-structured, kind of automated way you can figure out how to compute gradients of any, of the loss with respect to any things in the network. And given that the ability you can do that, basically, this is not something you ever need to derive. If you have software that can do that, you never need to derive this stuff again. So, and not every software package can do it, like scikit-learn cannot do it. So that's why we need to look at some new packages. And these are often called frameworks for neural nets or for deep learning. And there's a whole bunch of them. This is, maybe we shouldn't say popular today because I think this website hasn't been updated in a few years. But this was at least, I don't know, maybe like 2-3 years ago. This was, what were the popular ones? There's always ones that are coming and going. Some of these are no longer supported. Some of them are gaining in popularity. But you may have heard of some of these. The ones that are probably the most relevant today I think would be those. And we'll talk about at least 3 of them. So TensorFlow was basically like the first one that came out, the first software package that could really do all this stuff in a very general way, and came out in 2015. And because it's 10 years later now, this is very widespread. It's also very mature for deployment, which means if you really want to have a production model, like you're at a company, you want to distribute this, it has a lot of tools to do that. The original version was kind of cumbersome to use. They had a major update. It's better, but it's I think it's still not great based on what my grad students have told me that have had to use this. There is something called Keras, which is a great simplification that can run on top of TensorFlow or some other packages. And basically, it makes certain things super easy. Like one line, you can build and train a neural network. So it's like if you have a very common thing to do that's covered by Keras, it can do it very efficiently. But if there's an issue, because all the details are hidden from you, it's very difficult to figure out what's going wrong. Or if you want to do something a little bit different than very standard things, then it's not going to work for you. So, so that's Keras. We're not going to talk about Keras. We're going to focus on PyTorch. So PyTorch came out a little bit later than TensorFlow. But basically, they learned from the mistakes TensorFlow made, and they came up with something that was a lot easier to use. And it has grown in popularity, and actually today, it's much more popular than TensorFlow. And it's always been the most popular in like the research academic community. So, so that's the one we're going to focus on. And there's a few articles that are now, I guess, a few years old about differences between them that I've linked here. But what we're going to do for the remainder of this lecture is just kind of figure out or go through what PyTorch says is the recipe for doing this stuff, and we're going to use the demo of this unit just as the example for how we do all this in PyTorch. So basically you could say 5 main steps. We have to construct the data set and data loader, construct the network, select the optimizer and our loss, fit or train the parameters, and then finally apply the network. There's a lot of good tutorials on the PyTorch site if you're looking for more information, more depth. Basically, I'll just go through the steps. So the first step is constructing the data set and the data loader objects. So basically we have to import Torch. This is like the main package. And then we have to import some sub-packages. So the first important thing to talk about is data types. So when you work in NumPy, the NumPy's ND array is like the main data type you work with, right? It's like n-dimensional arrays. Everything you do in NumPy is an n-dimensional array. Well, everything you do in PyTorch is a Torch tensor. And the difference between Torch tensors and ND arrays is that basically Torch tensor it's like everything an ND array does, but it also has the gradients. So when you have one of these computation graphs, there is storage for the gradient as well as the value of those nodes in that Torch tensor. So whereas an ND array would just have the storage for the values. So that's one of the big differences. And so there's going to be, this is like, if this is starting with NumPy, going to Torch, you need to do this. And then, here we're renaming the variable xTorch to distinguish it from the original NumPy version. And then we'll need to come back later. Okay, so once we have the training features and labels, we can create what's called a tensor dataset, which we're using this command. And that has the right format to work with the data loader. And the data loader is very important because that is the thing that does all the mini batching for you. And it really automates it very seamlessly. So it's going to be in charge of So this is exactly how you do the mini batching. You have a for loop, and you do something like this. Batch is just an integer index. So you do batch, comma, data, and enumerate loader. So the loader is the thing, is our data loader. And what this is going to do is it's going to, every time you go through the for loop, it's going to pull out a new mini batch of data. And here we're splitting that data into the features and labels. So all that is handled here. And the cool thing about it is that it can handle this across multiple GPUs in the same machine, or even multiple machines across a network. It can coordinate all of them so that they're all doing the mini batching together in, you know, in a way maybe that they're like sharing mini batches of the same data set. So all that is basically hidden from you, which is great. You don't have to worry about that. That's just done automatically inside this data loader. You can also see here, this is where you have to specify the batch size. You have to tell it how big your batch is. Okay, any questions? Okay. Second step, we're going to create the network. So here we need a different package, torch.nn for neural networks. And the networks are described by these, in the object-oriented framework. You build a class of this NN module, and the class basically has two functions. It has the initialization function, and it has the forward pass through the network. In the initialization function, you're telling it like how many input nodes are in the network, how many hidden nodes, and how many output nodes. And then you're also internally, you're creating the blocks of your network. So here you're saying an activation is going to be a sigmoid. The first linear layer, which we're going to call a dense layer, to distinguish it from a convolutional layer, which we'll talk about in the next unit, is using this nn.linear. So this is just basically a matrix multiply plus that bias term. And then we're actually going to have two different layers. So we have dense 1 and dense 2. So we're setting those things up in this initialization. And then when we go through our forward pass, that tells us how we connect those blocks together. So here you can see if when you do a forward pass, you start with X, you put it through the first dense layer, first linear layer, you put that through the activation, and there's a lot of flexibility in how you write this. So here we're actually just renaming the original X as this new X, and then we're putting that new X through the second dense layer, and again, the same activation function, which is just a sigmoid. And finally, we get this out, and then we just return out. So that's setting up our network, its architecture, what blocks it's going to use. And you can see this is going to be flexible with respect to the number of inputs, number of hidden layers, number of outputs. So we can actually use this both for our demo as well as for MNIST, just by changing those things. And so here's where we instantiate that thing. So we call net, and we tell it this is how many input nodes, and number of features in X, number of hidden nodes, which is 4 in our case, and number of output nodes, just 1, because we have just binary classification. Right. So there's tons of these options available to you in terms of the different blocks in the network that have all been designed and coded in this package. Any questions? Okay. So, okay, what about the learning algorithms? So these are in the Optim package, and they have programmed a whole bunch of variants of stochastic gradient descent. So here's just a few of them, some of the more popular ones: rprop, rmsprop, AdaDelta, AdaGrad, Atom. Atom is by far the most popular. It's usually just the go-to thing people start with. Sometimes people will use a different one, but Atom is almost always used. If you would like to know more about how those algorithms are all designed, what makes them different, I put in a few links here. We're not going to get into any of the details, but basically they all have variants of like adaptive step sizes, maybe a different adaptive step size for every coefficient. They have things like momentum, which means as you're kind of moving, you keep moving in the same direction as the previous gradient, as in an attempt to just sort of not get trapped in the local minima, but if it's a shallow local minima, just force your way through it. So there's all these tricks that have been developed for these different algorithms, and you can read about them if you like. And here you can see is how we set up Atom. We have to basically tell it two things. We have to tell it which things do you want to optimize, and then we have to give it a list of any kind of specific hyperparameters for that algorithm. So in this case, we're setting the learning rate at 0.01. There's all kinds of other parameters in Atom, but we're just leaving them at their defaults. And then, so that's basically the learning algorithm. And then the loss, again, they've implemented tons of different losses. So this is one of them, binary cross-entropy loss. There's another one called cross-entropy loss. There's MSE loss, which is basically RSS or MSE. There's L1 loss. There's tons of these losses that they've put in there. And the cool thing is you can actually combine them just with like additions and scalings. You can make a new loss by taking two of these other losses and just adding them together. It knows what you want to do when you do that. Okay, so those are how we set up the optimizer and the loss. Any questions? Okay, and so now here's where we put everything together. So basically we have an outer loop over the epochs and an inner loop over the mini batches. In the outer loop, what we're doing is not very exciting. We're basically just setting up some error counters, which will allow us to count, how many errors have we, these are binary classification errors, how many have we seen so far as we go through the different batches, and how many total samples have we seen so far. And then we also have an empty vector that we're going to fill with the loss itself, so the binary cross-entropy loss values. So the inner loop is more interesting. So this is what I showed you earlier. This is how you draw the mini batch of X and Y. And then sometimes you have to do things like, okay, so this X batch is going to be a two-dimensional array, but the Y batch, just the way that the data is built, is just a one-dimensional array. Just an array of, I think, zeros and ones, from what I remember. But this particular criteria we set up, it does not like that. It wants Y to also be a 2D array, meaning, here we have, it's basically a column vector. So, and if you don't do that, it's going to throw an error. So here we're basically changing the shape from a 1D array to a 2D array in that line. So this is what we have for our batch elements. So now we can just put them through our model, put them through our network, and we get an output. Now, given that output, we can compute the loss. So here's our criteria, our binary cross-entropy. We give it the output of the network, and we give it the training labels in our batch, and it computes the loss. And we're just going to append that to this empty vector so that we can plot it later. Okay, so this is maybe the most interesting part here is how we compute the gradients with backpropagation. So basically, the first thing you need to do is just zero out the gradients, because if you don't, they just accumulate. And then loss.backwards performs the entire backwards pass. It goes through your entire computation graph, and based on the current values of basically your forward pass, it computes all the gradient terms and it just stores them all. So now they're all stored. And the next thing we do is we take an optimization step, which is going to take the stored values. Since we computed all the gradients, those are available for our algorithm to take one step of gradient descent. And then just to measure how well we're doing, we're going to do a hard decision by taking the output of our network and just rounding the output. Remember, the output's going to be a number between 0 and 1. We're just going to round it, which will force it to be either 0 or 1. We'll call that guess. And then we can look at the difference between guess and our data. So these values will, because these are 0, 1 values, they'll either be 0, 1, or -1. And if you take an absolute, it'll be 0 if we got it correct, or 1 if we got it wrong. And then so this is summing the errors across our batch. That's going to give us the total number of errors for this batch. So we're going to add that to the running count of errors. And we're going to also, add the total to the running count of samples we've seen. So this is what's going to happen. It's just going to go round and round. And every time we come back to the outer loop, when we call this, it's going to reshuffle the data. Okay, so that's basically how it works. And then we just, based on what we've computed, we can measure the accuracy, and we can eventually plot these things. Okay, so that's the most interesting part of PyTorch. A lot of details here, but you have demo code and examples. So when it comes to the lab, you can use this stuff here. All right. Any questions on anything here? Okay. So let's look at what happens. So if we plot the loss versus our epochs, we can see that the loss comes down very quickly, but then eventually it sort of plateaus. When we look at our training accuracy, we can see that this is, it's not very smooth necessarily, but it is, eventually getting pretty high and more or less plateauing. It's not exactly monotonically increasing, but it gets to a decent value, close to 90%. Okay, so then if you remember, this is what we're working on here. So you might ask, well, how did we plot this red and white color map? So essentially, what we did is we created a grid of 100 samples. Actually, no, a grid that has, it's a 100 by 100 grid, rectangular grid. And we, using this mesh grid command, which you might have seen in MATLAB, we basically created that grid, and then we vectorized those samples into one big long column vector, or one big long matrix, and we just fed that to our method. So we put those through our model, and we got our outputs, and then we basically just reshaped the outputs back into a matrix and plotted them. Let me point out one important thing here is detach.numpy. So remember, in order to get working in TensorFlow, we have to convert everything towards tensors. But then to come back and plot things in NumPy or matplotlib, we need to bring things back to NumPy. And that's what this .detach.numpy does. It makes it back into NumPy, and then we can just use NumPy stuff after that. Yeah, so those are the main things going on here. Any questions? Okay. What if we want to do other things like, remember these plots? They showed, for the hidden layer, they showed the different activation functions computed over the same grid of samples, here. So those things are inside our network, so we can't really access them directly, but what we can do is we can actually sort of recreate that network manually here. So we can take that data matrix for the grid, and we can put it manually through the first dense layer, and then put that through the activation functions, and we can actually get what we want to plot. And you can see we detach it, NumPy, reshape it to a matrix, and plot it. So that's how we're getting each of these pictures. Okay, any questions there? Okay. The other thing we're doing is we're plotting the actual values of the weights in the output layer. So how do we get those? So for this, you can use the state dictionary of our model. The state dictionary contains all the trained weights. And so here you can access them individually, like dense2.weight, get those numbers. And that's essentially, and then just plot them. Okay, so that's that. Any questions there? Okay. So with the same network, with the same code, all we have to do is change the number of input, output, and hidden dimensions, and we can apply this to MNIST. So we're going to use, if you remember, MNIST has 10 different classes, so we're going to use 10 as an output dimension. The input dimension is, I think, 384, and then the hidden dimension, we're going to use 100. This is something that you need to choose. Maybe it would have worked better with a larger number, but might have taken a little bit longer to train. So we're going to use cross entropy loss just like before, sigmoidal activation just like before, atom optimizer just like before, but this time we're going to use a smaller learning rate. We're going to use 50,000 of our MNIST samples for training and 10,000 for test. And this is what happens as we train. So here we're plotting the training accuracy. As you can see, this is going up almost to 100%. The test accuracy is plateauing around, a bit higher than 97. If you remember, 97 was what we got with the support vector machine with the RBF kernel. So this is doing pretty much as well as that. And maybe we could tweak things to get it to work better. But the big advantage of this over the SVM is if you wanted to test the SVM on 10,000 test samples, that would take a while, because for each test sample, it has to basically compute the RBF kernel value with every one of the support vectors. And there could be a lot of support vectors when you have 50,000 training samples. So doing that, computing this number for the SVM is going to take way longer than for this neural network. For this neural network, it takes time to train it, but once it's trained, inference is very fast, because all you have to do is take your data, do some matrix multiplies and some sigmoid evaluations, and that's it. It's extremely fast. So, that's the big difference over the SVM. Okay. Something interesting about neural networks is, in terms of the bias variance trade-off, when you look at this, you might say it's overfitting, and that the training accuracy is almost perfect, and then there's basically a gap. And so you might be tempted to say, well, maybe I should try to bring these closer together by perhaps removing some nodes from my network, getting different point of the bias variance trade-off. Well, it turns out that that is not really the correct design wisdom for neural networks. Neural networks seem to work best when you have them architected so that the training error can get close to 100%. So this is sort of what you want to see, or training accuracy close to 100%. You still need to play with stuff to see how high you can get your test accuracy, but don't think that, there's a gap here that I don't want to see. A certain amount of this behavior is actually expected or desired for neural networks. Okay. We'll talk about that more in the next unit. All right. Any questions here? Okay, great. So, so like the things we have to choose if we wanted to do better, maybe we would try a different number of hidden units. Maybe we would try, instead of sigmoids, some other version of an activation function. We could try a different optimizer. We could use different learning rates. We might even schedule the learning rate over the epochs, meaning maybe we start big and drive it small. We'll talk more about that in the next unit too. We might try a different batch size. And we might try more epochs if we thought that this was still getting better. Looks like we're using enough epochs, but and there's even other things you can do. You can use L2 regularization as a way of maybe preventing overfitting. And the way you do that actually is directly through the optimizer through a parameter called weight decay. So that's how you do it in these networks. You don't actually add things to your loss. You just directly change the weight decay on the regularization. And there's an interesting thing that happens when you're using ReLUs and you do this L2 ridge style regularization of your parameters, you actually get sparsity in the activations. The activations themselves become sparse. It's sort of an interesting thing that happens, the interaction of the ReLU and the that ridge type regression. Okay, so one option is to kind of go through by hand and tweak these and get a sense for what's working best. There's another option, is to use a package like Optuna, that's probably the most famous one, to tune all these hyperparameters. So both of these techniques can work very well or work very poorly depending on how you do them. So if you want to use Optuna, what you basically do is you tell it, like you give it like a list or a range of hidden units, a list of the activation types you want, maybe a list of optimizers, blah, blah, blah. You give it like all these possibilities for it to test, and then you let it run for a long time. Maybe like, weeks or something. However, it depends how big your network is, how big your training data is, and so on. But it takes time for it to really figure out, especially if you give it a lot of degrees of freedom. So what I've seen on the final project in the class, I tell you guys, like you guys can, if you're doing the neural network, you can manually tune these things or you can automatically tune them. Like I said, both can work good, both can work poorly. With Optuna, the issue is if you don't let it run long enough, it's not really going to give you a very good answer. So it's sort of like, and there's maybe a little bit of care in terms of setting up and using it. This can give great results if you give it enough time and resources, but if not, it's not really, you're probably going to get better results just by tuning things by hand. Because as a human, you can, you're smart enough to figure out like what seems to be working, what's not working, and so on. Of course, if you don't understand how all those things really fit together, then you might not get it tuned well either. But both of these are viable approaches that people use in practice. And the very last thing to talk about is, we talked about this before, is that remember how the loss can be defined for classification using the output scores. They're also called logits, or the output activations. Two ways to write the loss. This is the binary cross entropy loss in terms of the logits, binary cross entropy loss in terms of the activations. So when training your network, you have to make sure that you are choosing the right one. And so in PyTorch, if your network outputs logits, and this is binary, you want to use BCE with logits loss. On the other hand, if your network outputs these activations, like the one we did, then you want to use BCE loss. And if you use the wrong one for how your network is designed, it's not going to work that well. If you have more than two classes, non-binary, if you design your network with logits as the output, then you use cross-entropy loss. But if you actually put in that the softmax, and I think you actually want to even take the log of it, then you use something called NLLL loss, or NLL loss. So again, it's just have to make sure you're using the right loss for how you constructed your network. This blog post has some more details on this if you want. That's all I have for this unit. Let me know if you have any questions. If not, we'll see you guys on Friday.